I'm sure we've all heard of things like smartphones, smart homes, smart cars. Medicine is also getting smart. There's a lot of effort being developed in trying to develop analytics for medicine. So these days, anything you attach analytics to becomes smart. And so same thing with medicine. But to develop effective data science analytics for medicine, there are certain foundational data science problems, foundational energy barriers that needs to be overcome before you get this smart aspect working really well. And so today I'm going to discuss a little bit about the foundational issues, these energy barriers, as well as some of the solutions we have come across in trying to solve these problems. These are the disclosures. So just a little background, I'm a data scientist foundationally. I have a background in signal processing, image processing, and machine learning. And I've been fortunate enough to be able to apply the skill set in the field of medicine for the last 10 years. And so in doing so, I've become part of this research center called Michigan Center for Integrative Research in Critical Care, or MCIRC. You might have seen this slide earlier today in Dr. Kevin Ward's presentation. And so amidst all of the cores that we have, there's a small core there called the data science core. That's where I belong. And our main aim is to try and utilize the data that we capture from the patients in the hospital system and try and develop analytics that can go back into the same system and help not just the patient but also the caregivers in some fashion or the other. So particularly we are focused on critical care, as the name suggests, of the research center. So from the data science perspective, from the data perspective, what does critical care look like? You have the site of the incident or the accident, where essentially you have the least amount of data, but the caregivers there have to still perform certain things to ensure that the patient's doing okay, and they have to do this with void of data. And then you move on to the next echelon of care, they moved into the ER, ED, and then data seems to improve a bit, but still they have certain constraints, certain unique challenges within this sort of a system. Like, for example, time constraints. So they have to work in that sort of constraint to make sure the patient's doing okay. Then we move on to the OR. A lot more data can be achieved here, but they also seem to have certain unique constraint in which we can deploy analytics or try and help use the data that they measure from these patients. Finally, it's the ICU, so this intensive care unit, and this place happens to be the most data-rich environment you can get within the hospital. So as a data scientist, it was a natural tendency for me to look at places like this. Since we have a lot of quality data being captured every single day from these patients, why not start there, build analytics there, and then see how you can take it down the echelons of care and make it applicable even where data is less. This is a picture of a typical ICU. This is, of course, a pediatric ICU. We have a lot of instrumentation going on that small real estate. The same thing holds good even for adults. So there's a lot of data being captured, much of which things like lab data, nursing notes, physician notes, and so on and so forth, which is both structured and unstructured, does get stored. And does get stored in a very organized fashion in the EHR. But then data that's lost, even though it's measured, but completely lost, is everything in the box, in that orange box right there. So the physiological monitoring that we put on these patients, so ECG, arterial lines, ICP, and so on and so forth. So we tend to capture all this data because it's extremely useful. That's why it's in the ICU. But believe it or not, none of this is actually stored. And the reason it's not stored is simply because of the veracity of that data. So the data coming off of these physiological monitors can vary anywhere from 30 samples per second all the way up to 250 samples per second. So imagine all that data being thrown at us, and physicians and nurses who walk in have to literally look at all this data and assimilate and make sense of it all. And if we know it's useful, but making use of it is actually very difficult. And so that's one of the foundational energy barriers of doing proper data science when it comes to large data and when it comes to medicine within large data. So how do we solve this problem, right? So first and foremost, to give you a perspective on what data looks like in the field of medicine, let's take the example of stockbrokers. A typical stockbroker firm with all their clients store about 1 terabyte of data per day. A Boeing 747 flight, domestic flight, stores about half a terabyte of data just in a single flight. And then we have data from patients. Although we measure a lot more, we tend to store only a fraction of a terabyte. If you consider things like CT scans, X-rays and stuff, that does get inflated, but that's not a common thing across all the patients. And so in reality, we are really not storing the level of data we really capture from these patients. To solve that problem, MCirc decided to develop a foundationally different infrastructure within the hospital system in order to capture this data, this large volume of streaming data that comes from sporadic different sources. And not only does this infrastructure capture all of that, but also stores it. And in addition to all of that, it makes it available live in real time to get augmented into analytics so that these analytics can produce real-time feedback and goes back into the clinical setting where clinicians, physicians, nurses can utilize that in the caregiving process. So that's the infrastructure that we spent a lot of time and money on making sure it happens. And now what that has enabled us to do is tackle very important challenges within the critical care realm. And these are just a few of the highlight examples, but there's a lot more going on now that we have data. We have data from, for the past 2 years, from 175 adult ICU beds, and we have not let go of a single bit of data that's produced on these beds. So it's a wonderful trove of data that we've captured. And so these are some of the highlight topics, as I said. So we have this data, well and good. How do we do data science? Now, especially with complex data like this, which comes from different places, when we take any of these topics that I showed and we decide to build out an analytic that could perhaps help, there are very common fundamental steps that everyone has to take. And this is the 10,000-foot view of that. So you have data, complex different sources of data, but the data was never designed originally to play well together. These data comes from different sources, and they don't like each other usually. And so to be able to bring them all together in a harmonious manner, that's very important. And so the platform that we developed does that, does the legwork of trying to bring this data in a clinically, contextually meaningful manner, so that when we go back into this retrospective data, it makes sense. We're not worried about when was this captured versus when the drug was actually administered, so on and so forth. Now, once the harmonization process happens, it still sits in databases. It's Hadoop and SQL and so on and so forth. We do not want our physicians to be spending time in classes and Coursera and so on and so forth to learn how to utilize that data, to go in and dig and capture data that they want. So we have provided tools. This is, again, another energy barrier to do good data science. So we provided tools that abstracts all of that and in a very visual manner provides the data in a format where they can dig in, look through in a time scale of data coming through as and when it had happened, and then go into sections and regions of interest and annotate that for data scientists like myself. And once we have that clinical gestalt added upon the data that we've captured, data scientists can use that data as well. But data scientists need this data in a different format. And so there's a mechanism to do that as well. Formats that are conducive for Python programming environment, MATLAB, and what have you. So once all of this really comes together, which we have made sure it happened, you can actually develop something called a clinical decision support system. But developing a clinical decision support system on retrospective data is well and good, but it has to work in real-time clinical environments. Its efficacy must be tested with prospective data. And so this is where the infrastructure also enables that. So you have clinical decision support system that we've developed, tested on new patient live as and when the data is being produced from these patients, where physicians utilize the clinical decision support system and then give us feedback. And they say, oops, it's not working, and that's usually the case. So we then have to go back to square one, correct everything that was wrong, and make sure, try it again and see if it worked better next time. And it's an iterative process. It happens over and over again before a single predictive model actually predicts correctly. And so this is a typical fashion in which research happens with data science, but lots and lots of barriers to make this happen. So foundationally, if there's no infrastructure to enable this, it's an extremely difficult process. Luckily, at Michigan, we figured this out. We have this sort of an infrastructure that enables us to do this in a very iterative fashion. But that's Michigan medicine, right? Well and good. I mean, our patients tend to benefit from this in the long run. But what about where most of medicine is practiced? You know, in all honesty, most of medicine is practiced in community hospitals and resource-strapped places. So having to ask them to set up such a large infrastructure footprint makes no sense. And so earlier on, we started thinking, how do we take this to these community hospitals with the least footprint possible, this leanest possible deployment, so that just the analytics runs there and the physicians benefit from it while they're giving care. And so in order to do that, we've started migrating to the cloud. It's an active process, ongoing process. We're migrating the whole thing to the cloud. So not only does it allow us to deploy in remote places, but it also enables us to scale at will. But otherwise, scaling is always a big issue in such hospital systems. And so, as I mentioned, there are tools that we have developed. I'm going to skip through that, but here's one of the examples of the analytic that came out of such a infrastructure support, right? It's called AHI. Now, analytics for hemodynamic instability. I'm going to play a quick video. The idea of this analytic is to be able to detect hemodynamic instability well before traditional vital signs detected, well before that. And so what you see is you're continuously, every 2 seconds, you start getting these green, orange, or red bars, green indicating they're hemodynamically not compromising, they're fine, or they're compromising, the body is compromising, and then they're compromised to an extent where it's gone to the red, it's going to fail, the compensatory mechanism might fail at any time. So it starts giving you this indication, and you get to see the compensatory mechanism of the patients. Hemodynamically, are they struggling or are they doing better? And this tends to do much better than traditional vital signs. So we wanted to see how much better. We did clinical validation on hundreds of patients, but what I'm highlighting here is a recent cohort that we looked at. We wanted to see, we took a recent random set of 22 RRT cases, and we wanted to see how AHI would recognize a potential for RRT, given the hemodynamic status of these patients. And of the 22, AHI got everything right. The specificity right now, window-to-window specificity, is around 97%. More importantly, though, how early was AHI depressed into the red and stayed in the red before RRT? So on average, across these patients, it was about 15 hours before RRT was caught. So well before an RRT was caught, and RRT here is rapid response team, or a code call where a rescue has to happen. So well before that, we were able to recognize, just with a single lead of ECG as a data input, that something was impending for this patient. So this was very encouraging for us. Now the next product that came out of it, or a highlight project that came out of it, was called Barrel-I. So it's a clinical decision monitoring tool for traumatic brain injury patients. Now, we were trying to recognize the physiological component of the brain, how well the physiology of the brain is doing, but from the outside, right? So it so happens there's a fish called the Pacific Barrel-I with a transparent head, so you basically get to see the brain directly. And so I thought it was very fitting to name this product the same. And so this is what it looks like. Essentially, I'll start playing this video here. These are all actual patient data that we've used. So the bottom 3 rows here are indices, clinically valid indices. Everybody knows that in the literature it exists. People have explained how it works. It's based off of typical vital signs. And as you can see, these indices at the moment for this patient is saying green, everything is good. The top 2 are variants of AHI, which I just showed you before, and it's trying to predict where the patient is headed as far as their hemodynamic trajectory is concerned. And as you can see, those 2 seem to be saying red. I'm just going to forward this a bit, and you'll start seeing that you start seeing signs of red in the traditional vital signs-based indices as well. We'll move on, you start seeing more and more red. This is basically the body compensating, decompensating, compensating, decompensating, and to a point where the compensatory reserve is exploited completely, and the patient starts failing. And so in this particular case, the patient goes tremendously into the red, and a very drastic intervention had to be provided for this patient, but AHI was already recognizing the potential for that an hour before the intervention was provided. So another case where it was very exciting to see that an analytic can predict something like this. So in conclusion, I just want to say that there are tremendous amount of energy barriers to do good data science within medicine. And at MCirc, what we're trying to do is remove some of those energy barriers, or at least lessen them. And so really, when we develop science, when we develop these foundational science or analytics, what have you, our aim is to not just develop it for the benefit of science. We want to benefit patients from this. And so the translational path from bench to bed is extremely difficult. But we're hoping that with University of Michigan and MCirc and all put together, this kind of infrastructure really enables us to do this not just quickly and iteratively, but in an effective manner where it actually helps patients. Thank you.